Okay, let's continue. And so it is equivalent to the equilibrium check for the problems. And if we take the variation of the pi functions, one of the calculation methods, we replace this one into the u vector and calculate this one. Or you can take the variation of the pi and you can take the delta, the variation, which is very close to the when we take the derivatives. So if we take a variation of this, the first term, there are three matrices times multiplied together. You can use a similar theorem like the chain rule. So first you take variation of the first vector, multiply by the second and the third matrix unchanged. Then you need to plus take variation of the k matrix, but keep the first and the third vector unchanged. And plus the first two unchanged, take variation of the third. So if we take the delta pi, it will be the 1/2 delta u transpose k u. Okay, since the second and the third they are unchanged. Then we need to take the variation of the k matrix, but we cannot vary anything in the k matrix. When we calculate the k matrix, they are related to the geometry, those input xi and yi coordinates, and they are the known values. We cannot make any change of the input nodal coordinates. Also, when we calculate the k matrix, we need to use the material properties like the Young's modulus, the Poisson's ratios, and all those material properties, they are also fixed value. We cannot make any variations. So variation of the k matrix will be equal to 0. So we don't need to consider the variation of the second term. Okay, then we need to plus 1/2 u transpose k delta u. Okay, so that's we keep the first two unchanged, take variations of the third. And the second term, okay, the load vector cannot be changed. Only the u vector can be changed. Also, we should notice the first two terms, they are the scalars. Since if we multiply these three together, we will get a 1/1 matrix. For all the 1/1 matrix, if the transpose is the same, then we can prove these two values, they are the same. Okay, so we can add these two together. Okay, the requirement, if the u vector can give you the minimum total potential energy, then it should make the delta pi equal to 0. If the delta pi equal to 0, you cannot expect it is controlled by the delta u. Remember, the variations, they are the random and the very small changes of all the elements in the u vector. So you cannot expect the result equal to 0, which is controlled by this one. The only thing you can expect, if the results in the parentheses, which is equal vector. And in this vector, all elements, they are equal to zeros. So this one, inside the parentheses, should be equal to 0. Okay, so you can get okay, so that's the next things we need to do. If we know how to assemble the global K matrix, also you know how to modify the K matrix. And if you know how can we calculate the global load vector P and get the modified global K matrix, then you can go to the equation solver. You can use an existing package which can use the Gaussian elimination method to help you to get the unknown vector U vector. Okay, so after we calculate the K matrix, get the P vector, the next things we need to do is we need to solve the simultaneous equations and to solve the U vector. Okay, so actually I believe I have mentioned this before. It is I repeat, since it is the one of the important steps we need to finish. Okay, you can print the screen, then I will continue. Okay, remember the basic unknowns. They are the U vector. Okay, when we assume the displacement functions, they are controlled by those unknown nodal displacements. So after we solve the U vector is called the basic unknowns of our method. And the method we use is the displacement method to solve the problem. So the nodal displacements, they are always the basic unknowns. After we solve the basic unknowns, then we can go to the output. Okay, so it means after we solve the basic unknowns, the nodal displacement, then we will output all the required informations from the structure analysis. So what kind of results we like to output to the program user? Usually it includes the usually it includes the nodal displacement, and you can use the label like the node 1, 2, 3, U vector and the V vector. You just print out. Okay, so you can output the displacement for each nodal for each nodal point. So that's the results, and those results you can get it from the U vector, Then we can go to the what element. Okay, then we can go to a loop. We can go to all elements, and we can output the strengths and the strains in the elements. And right now we can use after we solve the U vector, and Okay, for the considered element, we can get the related u vector. The related u vector for this particular element, it will be the node points which are connected to this element only. So for a 4-node element, you can get the related 8 nodal displacements from the global displacement vectors. You just pick out the required displacements in the global displacement vector u and put them into a small vector, and for this one. And then we can use the b times u to get the string. Okay, so remember when we derive the element stiffness matrix, we use the shape functions to interpolate the displacement fields inside this element. Also, we can use the partial derivatives either to the c and the eta. Also, we need to multiply the inverse of the Jacobi matrix, and those elements represent the partial x to partial c or partial x to partial eta, something like this one. Oh no, they should be the, okay, yeah. They are the partial x to partial c, those. Okay, after we calculate all of these, then we can calculate a B matrix. The B matrix, they are still functions of the c and the eta. And if we change the c and the eta, actually we are changing the locations of the points inside this element. So if we know how to calculate the B matrix, then we can calculate the strings inside the element. And most of the time we will okay, we can, if we use this formula, we can output the strings at any locations, as long as the c and the eta, they are between -1 to +1. We can use all possible c and eta to calculate the B matrix. Then we can calculate the epsilon vector at the corresponding locations. But most of the time, we will output the results at integration points. Not only the integration points, they are used to calculate the K matrix, and sometimes they are used to calculate the equivalent load vector. Since we calculate the K matrix at the integration points, so based on the previous research, if we compare the accuracy of the output strings at the integration points compared to some other points other than the integration points, we found that the accuracy at the integration points, they are always better than those for other points. So that's why for most package, if you didn't specify, usually the program will output the strings at the integration points directly. Okay, and when we calculate the strain energy, we use the 3 strings, epsilon x and epsilon y, and gamma xy. Okay, But sometimes when we output the strings at the integration point, we will output also the epsilon z. Okay, remember, due to the Poisson's ratio, if we consider a plane strain, problems, the epsilon z, which is also non-zero. When you output the results, you can use the Poisson's ratio multiply to the epsilon x and to the epsilon x and epsilon y, so you can get the epsilon z. Okay, you need to use the correct formula. Okay, then we can calculate the strains. Okay, also we can calculate the strains. Also, the output of the strains, most of the time we will output the strains at the integration points. Okay, so we can multiply the calculated strains by the D matrix, then we can get the sigma. Okay, so if you like, you can also calculate the reactions at the suppose. But for the finite element method, usually the reactions it is not so important for the program user. Okay, so that's the results we need to output and print the screen. Then I will continue. Okay, I have finished all the things I like to tell you about the plane straits problems, and also that's the only element and that's the only problems I will give very detailed discussions, no matter how to calculate a small K matrix. How can we assemble the global K matrix? How can we calculate the load vector for elements? And how can we assemble those local load vectors into the global load vector? And I didn't give you the detail about how can we solve the simultaneous equations. In another course of this semester, I have discussed the Gaussian elimination method. Usually, we will use the Gaussian elimination methods to solve the simultaneous equations. Okay, but you can. I think it is it is quite easy to find the existing package which can help you to solve the unknown vectors. And then what kind of the results we need to output. That's for the plane straits problems. And later I will talk about the other elements and the other problems. But for other elements, I will mention only the topics which are different from the plane straits problems. Okay, so we have the so-called 2D problems or 2D elements. Okay, a typical two-dimensional problems, which is the plane straits problem. Okay, why the plane straits problems is called the two-dimensional problems? Remember, we need to use the XY coordinates. And the XY coordinates, they are defined on a plane. And we will use the defined XY coordinates to describe the geometry of the structure we will use the xy coordinates to describe the displacement functions, the u and the v functions. And there are always two components, either for the location coordinates or the displacement of a point. And the two-dimensional problems usually means that we can use a two-dimensional coordinate systems to describe the geometry, the applied loadings, and the solve the displacement. For those kind of problems, they are called the two-dimensional problems. Under the plane straits problems, it is a typical two-dimensional problems. Okay, the second two-dimensional problems, which is the plane strain problem. The third one, which is the axis symmetric. Okay, so after the plane straits problems, I will introduce the other two-dimensional problems, the plane strain problems and the axis symmetric problem. And for the plane straits problems, remember all structures, they must be the three-dimensional structures. So although we use only the xy coordinates on a plane, but we still have the dimensions along the z direction. For the plane straits problems, it is a thin plate. The thickness compared to the dimensions on this considered plane, the thickness is always relatively very small. So you can say, how do we define which is a thin plate? You can say the dimensions perpendicular to the xy plane. The thickness is always relatively small dimension compared to the dimensions on this plate. Okay, so that's the geometric characters for the plane straits problems. Then let's consider what kind of the problems can be called as the plane strain problems. The plane strain problems, it is three-dimensional structures. A typical plane strain problems, which is a tunnel. Okay, the tunnel structure. Okay, we have the cross section. We have a cross section of the tunnel, and for the plane strain problems, you can say we can cut a cross section. We can cut a cross section of the tunnel, and if we cut the cross section, you can say the cut cross sections, the geometry, the applied loadings, and the boundary conditions, they are exactly same. It must be assumptions. You cannot expect any real structures. If you cut the cross section, even the applied loadings and the boundary conditions, they are exactly same. But that's why we say the structures, they are the structural models. whenever you mention the plane stress problems, they are the plane stress models, and whenever we mention the plane strain problems, they are based on the plane strain model. Okay, remember, they are structural model. The structural models, they are always different from the real structures. Okay, you should not expect there is any real structure which is exactly fulfill the assumptions of the structural model. The structural models, they are always simplified assumptions. We have since we like to neglect for some terms in the strains or some terms in the stress, so we need to make simplified assumptions. The structural model always use the simplified assumptions. Also, that's the reason we cannot expect the structural model can be the real structure. Okay, so whenever we cut the cross sections, you can see the geometry of the structure. The applied loadings. Okay, so probably we will see some loadings applied to the structures. Okay. Also, the third thing is the boundary conditions. Okay, so there are three items: the geometry of the structure, the applied loadings, and also the boundary conditions. And the boundary conditions of a tunnel, they could be the elastic spring support. Okay, so that's the most of the time that's the assumptions of a structural tunnel. We have the loading applied from the top of the tunnel. We have the lateral pressures, either from the soils or from the water. And we have the lateral pressure applied to the left and the right. And the boundary conditions, they can be assumed as the distributed spring supports around the bottom half of the tunnels. And that's the assumptions. And also for compared to the plane stress problems, the thickness T, which is a relatively very small dimensions, but for the plane strain problems, usually we will say this one is the XY plane. So remember, the XY plane, they are defined on the cross section. The XY plane, which means the plane of the cross section, and we have the Z direction. The Z direction, which means which is the axial of the tunnel. Okay, the dimension along the Z direction Okay, I will, since some of my students say they cannot read very clear about what I wrote on the whiteboard, so I will read them. The dimension along the z direction, they are much greater than the dimensions on the xy plane. Okay, the dimensions on the xy plane means the dimensions of the cross section. The dimensions of the cross section, they are relatively small dimensions. The dimensions along the z directions, the axial direction of the tunnel, the dimension along the z direction, which is much larger than the dimensions on the xy plane. Okay, that's the assumptions of the plane strain problems. So remember the basic assumptions of the plane strain problems. If we cut the cross section, no matter where we cut, all these three, they are exactly same. Okay, so the geometry, we can see the applied loadings of the structure, the boundary conditions, they are exactly same, no matter where we cut the cross section. Okay. Also, the dimension along the z directions, it is relatively much larger, or you can say in our simplified assumptions, the dimension along the z direction, it is close to infinity. Okay, so that's the assumptions. We can say the dimensions along the z direction compared to the dimensions on the xy plane, it is a much larger dimensions, and the much larger dimensions, sometimes you can say it is close to the infinity. Okay, so you can print the screen, then I will erase. Okay, remember the dimensions along the z direction. That's the z direction. That's the z direction. The z direction, which is perpendicular to the cross section. The dimension along the z direction, they are infinity. The dimensions, they are infinity. And at any cross sections, the geometry which is unchanged. So also the applied loadings, they will always be same. So if we cut a cross section, and in this, if it is a plane strain model, for these structures, if we say there is a concentrated load P, okay, if on the cross section, we for the plane strain problems, if we consider a concentrated load P which is applied at the tip of the tunnel cross section, then in the three-dimensional three-dimensional problems, what will be the P what kind of loading, which it can give you a concentrated load P in the cross section. Then you remember the basic assumptions. No matter where we cut, the loadings, they are exactly same. So a concentrated load at the cross section, it will be a infinitely long line loading. Okay, it will be a line loading, and the line loadings, which is applied on the tip of the tunnel. They since only for such kind of the loading conditions, you can always see a concentrated load no matter where you cut the cross sections. Okay, so that's the basic assumptions of the plane strain model. Okay, but there are some important characters you need to figure out by yourself, and I will ask questions, and I will not give you the answers. I hope all of you think about this, and I will discuss them in the next lecture. Okay, so if it is a cut cross section, it is a cut cross section of the tunnel, and I will. My question is consider the points on the cross sections. Okay, the points. If we take a lateral view of the tunnel, my question is the displacement of all the points. For the points on the cross sections, and if you understand all the assumptions about the plane strain problems, we have the assumptions. The cross sections, they are always same, no matter where we cut, and the geometry, the applied loadings, and the boundary conditions. Also, it includes the material properties. It will not be changed. So, no matter where you cut, everything is the same. Then, in this case, for any cut cross sections, where will the points move along the z directions? I will give you three choices. First, which is positive, w greater than 0. And I will use the u, v, and the w represents the displacement along the x, y, and the z direction. So the w represents the displacement along the z direction. The first choice, which is the w is greater than 0. The second choice is the w is less than 0. The third choice is w equal to 0. Okay. So my questions, and I will ask all of you think about them, think about these problems, and okay. And the next lecture I will tell you. But I wish at least some of you you can respond in the YouTube videos, or you can respond it to the Moodle. Any just any place you can respond and tell me what kind of the choice you make for these problems. Okay, so I will finish the lecture right now, and